Okay, if you want to hand in your homework, you have to do it now. Now, any questions before we begin? The midterm will be this Saturday at 1:30, as it was announced last lecture. And the place will be, we will be in this building, you will be spread out in U1, U2, and U3. I will send you a list of students who will be taking the midterm in U1, in U2, and U3. And the lists will also be posted on the windows in this building. Other questions? You are responsible for everything that we cover until Saturday. Well, you will learn it on Saturday. Well, you will have 3 hours, which should be much more than enough. Any questions about the physics? As? Well, we are not yet studying gravity. We will study gravity in several weeks. Well, we never know anything completely. Everything is subject to experimental verification, and things that we believe are true now, maybe tomorrow they will turn out to be wrong. Just look at the Newton theory, Newton dynamics. For many years, for centuries, we believed that they were the correct theory of nature, but then we discovered that they are valid only within a range of phenomena. And if you go beyond that range, beyond that limit, we have to use a modified version of Newton's laws, let's say. We have to use a special theory of relativity. And we don't yet know what are the limits of special theory of relativity, whether there are or not. And one day we might discover in the experiments that even special theory of relativity, or more generally, general theory of relativity, doesn't really correctly describe nature. We don't know. So in that sense, no physical theory can be verified. Okay, in that case, let's continue with the applications of Newton's laws. To circular motion. Now, we had already described the kinetics of uniform circular motion. And we know that what we mean by uniform circular, well, what we mean by circular motion is just the object moves on a circle. As an example, you can just take, let's say, this mass at the end of this rope. This is doing circular motion. It's not uniform. Well, let me shorten it a bit. It's not uniform, nevertheless, it is doing circular motion. It stops, goes back, goes forward. That's a circular motion. Now, when we say that a motion is uniform, we say that its speed is constant. So this is uniform circular motion. Its speed is almost constant, let's say. It's now doing uniform circular motion. And we had already discussed that if an object is doing uniform circular motion, this is the trajectory. Let's say it's moving in this direction at this point. its velocity vector is always perpendicular to the radius vector, because otherwise if it was not perpendicular to the radius vector, it would mean that the radius vector, the length of the radius vector would be changing. So the component of the velocity along the radial direction, along the radius vector, is the change in the radius vector, is the elongation of the radius vector. We know that the radius vector is not elongating, it has a fixed length, so the velocity along that direction has to be 0. And we also discussed that this is the velocity, and this object is doing accelerated motion because although the speed is constant, we said that it's uniform, so the speed is constant. Nevertheless, the direction of the velocity is changing. So at this point, the velocity is pointing upward. At this point, it is pointing towards the left. Here, it is pointing towards the right, etc. So the velocity vector is always changing because its direction is changing. Remember, a vector has both a direction and a magnitude. So although the magnitude is not changing, the magnitude of velocity is what we call the speed. Although the magnitude is not changing, since the direction is changing, the vector is changing. So if the velocity is changing, that's such a motion we call accelerated motion. There is an acceleration. And we also had discussed what is the magnitude of this acceleration, the direction of this acceleration. We said that the acceleration was pointing toward the center, and furthermore, the magnitude of the acceleration is related with the speed and the radius of the circle. Now, of course, if you look at this expression, it seems that there is a problem. What happens when r goes to 0? Is it not defined? But if r is equal to 0, it's no longer a circular motion. It's not a circle, so it doesn't make sense to talk about circular motion if r is 0. It's just at rest. So whenever we have an object doing uniform circular motion, in fact, whenever we have any object doing circular motion, there will be a component of acceleration pointing towards the center with this magnitude. Well, if it is not uniform, if the speed is changing, it will just tell us that there is also another component of acceleration in the tangential direction which will change the magnitude of the speed. This acceleration is responsible for the change in the direction of the velocity. You might have a tangential acceleration which will be responsible for the change in speed if it is not uniform circular motion. Now, any questions up to this point? Okay, now comes into the game the Newton's second law. So we had said in Newton's second law that the acceleration of an object, so if this object is doing uniform circular motion, we know that there is an acceleration. The acceleration of the object is proportional to the force acting on it and inversely proportional to the mass. So here we have an accelerated motion. So the question is, what is causing this acceleration? There has to be some kind of a force causing this acceleration. Furthermore, since the force is equal to mass times the acceleration of the object, and we know that the acceleration of this object doing uniform circular motion is towards the center, this force has to be towards the center. There is no outward force. The net force acting on this object should be towards the center, and the magnitude of the net force should be equal to mv squared over r. If there is no such force, in that case the object cannot make uniform circular motion. Now let's do an example. Let's just think about the simplest possibility. So you take a string and attach a mass at the end, and you start rotating it horizontally. So this will be more or less uniform circular motion. So, and in this case, what is the force? Can you identify the force? What is the cause of the force acting on this mass over here? is the tension of this wire. So we have this mass. This is the trajectory of the mass. It is attached by a string, let's say of length r, to a fixed point. And this mass is moving with a velocity speed v. So if we draw the free body diagram, here is our mass. But at this instant, there is just a single force acting on it, and it is horizontal. But at every instant, there is a single force acting on it, and it is horizontal. And it is the force due to the tension. There is no outward going force.
What about the weight?
Well, it is horizontal. So we will assume that it's horizontal. So the weight, we will study the weight later on. We will study this problem, for example. In that case, we will have to take the weight into account. But nowadays, let's just imagine this is an empty space. There's no weight, there's no gravity, there's no other external object, there's just a string and the mass. So if this is the tension, then we know that the tension has to be equal to mass times the acceleration of the object. If two vectors are equal, their magnitudes should also be equal. The magnitude of the force due to tension is equal to the tension in the string. This should be equal to mass times, the acceleration of an object that is doing uniform circular motion, we just said that mv squared over r. So this is the tension. So the faster you rotate, the larger the tension will be. Well, that is your everyday experience also, no? So if you just attach a mass, hold it by a string, if you rotate it faster, you have to hold it even stronger. Or if the mass is larger, then you have to hold it even stronger. So let's just imagine this one. So if you just rotate it, if it gets faster, you have to hold it faster. Now, any questions on this? Okay, now let's study a more realistic example, something that you have already experienced. Suppose you are driving a car or you have taken one of these minibuses, the bus is moving, and the driver just steers right. So you are just moving straight. At that instant, the driver just steers right in a very sharp turn, and he's really fast. So what is the direction of the force that you feel? To the right or to the left? To the left. This is the question. This is the car moving. You are sitting in the car, and the car just turns right. Let's try to draw your free body diagram. Your free body diagram.
There is no force because it's just a length.
There is no force, okay? So this is the right. So you said right, left. You said right.
I said it's right.
Okay, let's put it this way. No force. A, no force. Just inertia. Let's say this is F1, F2, F3, F4, F5, F6, F7, F8. So who think? Yes.
Friction force of seats.
What is the net force acting on me? I'm also turning right with the car. So what's the net force acting on me? It can be due to friction, it can be due to something else, etc. I don't know for the time being. What is the force acting on me? Okay, F3, F3, F3, F6, 6, 3, 3, 6. Anybody else? 6 or 3? 6. Okay, let me see the hands for those who think it is F6. What are, and those who say it is F3? Okay, more or less equal. Why F3? Yes?
I think
3 and 6 are equal. Okay, what is F3? What is F6? No, I'm asking for the forces acting on me. There's only one on me. So these action-reaction pairs, they act on different objects. So if there's a force acting on me, of course, I'm exerting a force on that something else, and they are in opposite directions, but there's one force acting on me. The other force that I'm exerting is acting on something else. So what is the force acting on me? So, because I will accelerate only because of the forces acting on me, not because of the forces that I exert on something else.
Centripetal force?
Okay, centripetal force, so you are saying F3? Okay. Why F6?
When the car turns, the object or this car moves relative to car, so there must be a force.
Okay, so you are saying that you are taking a reference frame fixed on the car. So the car, the object moves towards the left in that reference frame. So there has to be this force, this F6 force in this reference frame, okay?
F6 because the car is my reference frame.
Okay.
The chair I'm sitting on will the friction of F3 with the car. So the friction between me and the chair should be in the opposite direction. The friction is the source of my acceleration. So I will run the F6 direction.
F6, okay.
Experiment. I think I want to say F net is toward F6.
F net is towards F6, why?
I just thought about F3 because of just the centrifugal forces, right? But from experiments, daily life experiments, we know that when we have that sharp turn, we go to the opposite side. For example, we can go right side to the window. We can actually hit our head to the window.
You will lean to that side, okay? That's true, that's everyday experience of all of you.
Well, from the velocity change, I think that the force acting on me should be S3
Why?
because of the Newton's law force. Net force equals mass times acceleration. So acceleration should be in the direction of F3 so that my velocity will change from that to that.
What is the direction of my acceleration? Towards the center. Towards the center. So does anybody think that my acceleration is in the direction of F6? My acceleration is in the direction of F6. F6. Okay, let's see. Let's go one by one. Some of you were mentioning that, a couple of you were mentioning that if you are, according to a reference frame on the car, so you are the observer, let's say, and your friend is sitting over there, you are sitting over on some other seat, and you see that your friend will lean on the other side. That is a common observation, right? You all agree that that is what you will observe. So you are sitting, you are here, your friend is over there, and the car just turns right. So your friend, you will see that your friend will be moving towards the left. That is common experience. So you would say that, okay, if the object is moving in that direction, then there is an acceleration in that direction, and hence the force, there has to be a force in that direction, which is F6. What is wrong in this argument?
It's not an inertial.
It's not an inertial reference frame. Newton's laws are valid only in inertial reference frames. And the force is defined only in inertial reference frames. You cannot use the reference frame fixed on the car to define a force, because in that reference frame, Newton's laws are not valid. Is this point clear? Now, of course, if you still insist on using this non-inertial reference frame, you can still do that. But what you have to do is just add these forces that are not really forces. They are not in the strict sense, there is no such force, but still system. In that reference frame, objects seem to move as if there is a force. These are called fictitious forces. They are just fiction, they don't exist. But nevertheless, if you want to use that non-inertial reference frame, you can still do that. The force in that, this fictitious force, non-existing force, is in the direction of F6. But in this course, within this year, you are not allowed to use non-inertial reference frames. So for us, we will never be using fictitious forces. All the time, we will be dealing with real forces. And to define a real force, we always have to first choose an inertial reference frame. In non-inertial reference frames, we cannot define forces. Now, an inertial reference frame is a reference frame fixed on Earth. What is your initial velocity? Now toward that direction. This is your initial velocity. What is your final velocity? Downward. This is the change in your velocity, which is proportional to your acceleration, average acceleration, which itself should be proportional to the force acting on you. So the force is in the direction of F3, not F6. Okay, then why do you lean to the other side? What does it mean?
Because we want to stay as the state that where we want to stay there.
Okay, so why do you lean?
So, because our previous state was towards the left, but we are pulled to the right, but we want to stay in the left position, so we lean towards that. I don't know the physical nature.
Okay, do you all agree? You see, again, the problem over here is your different parts of your body are feeling different forces. The part that you are sitting on, your back, is mainly feeling the force due to the friction, which if you are not sliding, it will move with the car. But your head is just feeling the force that your internal muscles should exert. Your muscles should exert a force on your head if your head is also to move with your bottom. So that's why if you don't exert that force, if you are in a relaxed state, the chair, as it's moving to one side, it will carry, due to the friction force, it will carry your bottom to the same side, but your head will not follow. So in that case, you will just lean to the other side. It's not because there is a force pushing you back. Let's do an experiment. Just take one sheet of paper, which you will also use for a quiz later on. Now take an object which ideally will not roll and put it on this paper. That's what we will be pulling it fast, so I don't want it to roll. Mark its position. So where is it? put your hand. Okay, just like taking a curve, you are sitting in the car, just imagine you are sitting in the car, and the guy driving the car just hits acceleration. So the speed of the car will increase. So if you use the analogy with the rotating car, you will feel a force, this fictitious force that is pushing you back, right? If the car is speeding up, you will feel as if you are pushed back. But nevertheless, what is actually happening is that the seat is pushing you forward. So let's just do it here. Take this paper, mark the position, and if this was a car and you are sitting on this seat, you should be pushed back. You will feel as if you are being pushed back. But if you just pull it, you see, you didn't go back. You went forward with the car, with the paper. Don't push it so hard. If you push it so hard, it won't move. Do you remember the video that we watched of two masses? It's exactly the same story. No, not exactly the same story. We didn't discuss why it happened, though. Now, let's forget about the mass. Now, any questions on this one? The force is always towards the center. And there has to be, by the way, there is no such force as mv squared over r also. I'm not drawing another mv squared over r pointing outward. There is only a single force acting on it, which has to create this centripetal force so that the object will make circular motion. There is only a single force acting on my mass. True.
Why doesn't it move towards the center in a line like this and it just takes a circle?
Well, it has a velocity.
Because it has a velocity, it doesn't move towards the center.
Well, you see, the velocity of an object is not necessarily parallel to the force acting on it. It's only the acceleration is parallel to the force acting on it. But the motion, the trajectory will not be determined by the acceleration, it will be determined by the velocity mainly. How the velocity changes. So you see, this object is actually trying to go to the center, but at the same time it is moving upward. So that is why at next instant it will move towards the left because there is a force towards the left, but at the same time it is moving up. So it is now at this point.
O zaman bu dairesel, o iki tane vektörün dairesel hareketin vektörleri olduğunu düşünebilir miyim?
Okay, the vectors, which two vectors?
One velocity vector and towards the center vector.
Okay, both the acceleration and the velocity vector, they will also rotate, keeping their magnitudes constant. So in a sense, if you just take all the velocity vectors and put them such that their endpoints are at the same point, the tips will all go around the circle.
I have another question. What if the speed wasn't constant?
Let's do that. Let's do another example. I'm sure you have all watched these stunts where there's a motorcycle rider and he goes really fast and he goes around this circular road. Now, of course, in this case, let's say, let's just imagine that this is a bitter circle. So it comes here, goes around the circle, and then comes down. Let's just analyze the motion. Let's say here. He's right at that point. He will have some velocity. Now the velocity vector will always be tangent to the trajectory of an object. It will be always tangent. In this case, the trajectory is fixed by the rod, so the velocity vector at every instant will always be tangent to the rod. What are the forces acting on us at that instant? There we have gravity. There is the weight. There is the normal force. Let's ignore friction. I mean, if there is friction, there will of course be friction. Any other force? There is no centripetal force. There is no such force. It doesn't exist. This is it. There is no other force. There is no other force pushing it outward. There is no centripetal force. Let me correct it. There is no independent centripetal force. The sum of all these forces should be creating my centripetal force.
So there is a centripetal.
There is no separate centripetal force, separate from these forces. So in the free body diagram, there is no centripetal force. Well, let's see. At this instant, again, let's just choose some coordinate axis. Let us choose the one perpendicular to the rod and the one tangent to the rod. Let us call this one the x-axis, this one the y-axis. So over here, this will be the y-axis, and this is the x-axis. Now, of course, at this instant, the normal force is in the x direction. The friction force is, no, the normal force is in the y direction. The friction force is in the -x direction. The weight has both components, both the -x component along the -x direction and another component along the -y direction. So, we will not be doing too much details yet, and we will be studying this example in more detail later on. Let's call this omega x, omega y, and then we have here the omega x. So omega will be omega x plus omega y. Well, when we calculate the total force acting on my object, I have to sum all of these three forces. Well, there will be a component in the x direction, plus there will be another component in the y direction. Now, of course, if at this instant, at this sketch, the total force in the x direction is negative, so this has a friction force in the -x direction. The weight, the x component of the weight is also in the -x direction. So the total force, the x component of the total force is negative. Now, so since we have these two components of the force, one tangent to the trajectory and the other one perpendicular to the trajectory, our acceleration also has two components, one tangent to the trajectory, which is the tangent acceleration, and the tangent acceleration will be nothing but the tangent force divided by the mass. And there's also the central acceleration, which is the central force divided by the mass. But we already know what the central acceleration has to be. The central acceleration has to be v squared over r. At this time, v is the speed at this instant. So because the speed will be changing, so at any instant, if you want to calculate the, let's say the central force, you have to use the speed at that instant. Now we will be analyzing this more general situation later on, but a simple case we can just analyze now. Let's take the same example. The radius is r, it's circle. We are over here m, so it has some speed v, a velocity v. So what is the minimum value of v, of the speed, such that the mass follows the trajectory? And doesn't fall down. Yes, your question now. No, sorry. That's a typo.
The normal force has to be zero in this case, so mg times x or y, whatever, should be equal to mv squared over r times x.
Why should the normal force be zero?
This is the minimum case.
Why? Okay, your friend is saying that, okay, this is the question we have, but if you want to use some mathematics, some arithmetics, let's say, we first have to express this question in a mathematical form itself. Now, the trickiest part in this question is, what is the mathematical expression corresponding to not falling down? How can we express that condition?
We take y-axis upwards, y-axis down, y-axis, the forces on y-axis equal 0.
Okay, we will write the forces later on, but let's first try to understand the problem in general. What is the condition for saying that something doesn't fall? I mean, for example, if you tell me that okay, something is moving up, I can say that okay, the vertical component is larger than 0. If I chose the upward as my positive direction, that would be the mathematical expression corresponding to my equation. What is the corresponding? What are we trying to prove here? Oh, this is expressed in terms of words, but how can we express the same thing in a mathematical form? Tension? Which tension? There's no string over here. Well, I suppose you meant normal force.
You could say that gravity is being used as a centripetal force, which is why the effect of gravity is zero on the mass.
The effect of gravity is never zero on this mass.
It is if it's being used as a centripetal force.
No. If the effect of gravity was zero, then it would never fall down. But if net force is zero, it will not accelerate. It will neither curve down nor fall. It will not fall down, that's true, but it also will not follow this curve. Because if it is to follow this curve, it has to accelerate. The velocity has to change its direction. So if there is no acceleration, the velocity will not change its direction.
For something not falling down, either it is going up or there is a force that stables the gravity.
Okay, I repeat, your comment is just like hers. If there is a force stabilized balancing gravity, that you are saying that there is no net force acting on it, then there is no acceleration. If there is no acceleration, then the object will not curve along the trajectory.
But only in that direction. So, because it's a motorcycle,
Okay.
it shifts itself from the ground,
So let's ignore friction. Let's ignore friction. In that case, we don't even need a motorcycle. You just throw some mass along this loop. So there is no pushing or pulling, etc. You can still do this in the absence of friction.
Bu dairenin üstüne doğru çekmesi gerekiyor. Daha fazla çekersen düşer. Ya o kadar olmaz.
Well, let's draw the free body diagram for this one. At this instant, what are the forces acting on it? Ignore friction. There is the weight. There is a normal force. Any other force? So which one of these forces is pushing it up? Yes.
O yer çekimi kuvvetinin base şu dairenin üstüne doğru çekmesi gerekiyor. Yukarı doğru olan başka bir kuvveti yok. Eğer zaten bir kuvveti olsa yukarı doğru çekmesi.
Okay.
İşte bu dairenin üstüne kadar olması gerekiyor. Yer çekimi.
Ama bunu dengeleyen bir kuvvet olması.
So what is the condition in that case? In fact, your friend had said it already. The condition for the object not to fall down or just barely pass through should be n equal to 0. But why? Why is there a normal force at that point to start with?
I think the normal first reason to do. When we add the velocity vector and the weight vector,
No, hold on. Adding the velocity vector and the weight vector, why do you add them?
Because
Let me first ask this question. What is the unit of velocity vector? What is the unit of the weight vector? Newtons. You cannot add something that has a dimension, meters per second, with something that has a Newton dimension.
the object is falling down, but not in perpendicular direction because of the velocity vector.
Okay.
It is going left and going down.
Well, at this instant, it's not going down. There's no velocity in the vertical direction. It's only accelerating downward. At the next instant, it will be moving downward, but at this instant, not yet. There is no vertical component of velocity.
Or fake, as we said before, acceleration force.
No, there is no fictitious force. Forget about it. I don't allow you to use fictitious forces. They don't exist.
It must be equal to G actually.
No, there are no fictitious forces. These are the only forces there.
Its acceleration is such that its radius is less than or greater than or equal to r.
So, what is the condition? Which acceleration? The central acceleration should be less than or equal to
V squared over
v squared over r. Why?
greater than or.
Greater than or equal. Why?
Because if it's less than V squared over r, the mass makes a circular motion with smaller radius, so it will fall down from there.
Well, these two things are equivalent anyway. It's a larger than equal. Any other comment? So let me ask you another question. Why is there a normal force when we are at that point? I mean, we already discussed the normal force when we had this thing sitting over there, let's say. So we see that there is no acceleration, but we already know that there is the weight acting on it. There is a downward force, so there has to be an upward force. So which is we call the normal force. Now here, this situation is just the opposite. Just like this is our motorcycle or the mass. This is the road. The road is pushing it downward. That's what the normal force is doing. It's pushing it downward. Why? Why should the rod push it downward?
Okay, it's going to be a long explanation. But what I think is that the normal force, when we begin the gamma motion, wasn't the force that accelerated the object upwards in the first place. So the normal force at that point should be zero, so that the object will not accelerate downwards from that forward trajectory.
Can you repeat your last argument? Can you repeat your last argument?
What I said is that the normal force at the top should be zero, so that it won't be going downwards. It won't go out the forward trajectory. It will
So you mean if it is larger than zero, it will just fall down?
This is force asking.
Okay, so so the normal force shouldn't be non-zero if it is not to fall down, it is to follow this rod.
Yeah, it can actually. It can be. It has to be zero.
Otherwise, it will fall down. Okay.
I think that like in this system, there are two accelerations, tangential acceleration and central acceleration. Central acceleration is caused due to the weight.
Well, at this instant, we don't have any tangential acceleration. All the forces are in the central direction. So we only have the central acceleration at this instant.
Tangential acceleration is zero.
Yeah. When it was over here, the tangential acceleration is non-zero, but at this point, the tangential acceleration is exactly zero. Because there is no tangential component of any of these forces at the top. Now, let's see what happens if there was no normal force. Let's forget about the rod. Let's forget about the normal force. What are the possibilities? So let's see. The velocity might be very small, or even zero. If the speed was zero, it will just fall down. This is the v equal to zero case. It can be small, but non-zero, so it will have such a trajectory. Now, these orange lines are, I ignore the road, I ignore everything. I'm just assuming that I have this projectile over here, I send it with some speed v, horizontal velocity. If the speed is small, it will just move like this, so it will just fall down. If the speed is larger, it will fall further away. If the speed is even larger, it will just go straight, almost straight, and then accelerate downward. It will just follow a parabola. This is only under the influence of the weight. There's no other forces, there's just the weight. So you see, if the speed is zero, whether there is a road or not, it doesn't make any difference because it's just falling down. There's no contact anymore. There's no force that the road acts on. Well, if the speed is larger, well, still there's no contact afterwards. So there won't be any force exerted by the road on our mass. Let's assume the speed is very large. Well, if there is a road, my object cannot move like that, cannot move in that direction. So the road should exert some force on my object so that its velocity will bend. There will be a larger downward component of the acceleration if the speed is too large. So if the speed is too large, there has to be some normal force to keep my mass following this trajectory rather than following this orange trajectory if the speed is too large. That is why we have the normal force. So I say, there is, in these cases when there is falling down, there is no normal force. Well, there's no contact to have a normal force. If the speed is very large, then there has to be a normal force to keep my object following this trajectory. So if my object is not falling at this point, then the normal force has to be larger than or equal to zero. Almost equal to zero, let's say. N equal to zero is the limit at which there is a normal force. My object just barely goes around. Now the total force acting on my object, let's just choose one direction. Now the normal, let's just choose, this is my, let's say x direction. Then the total force acting on my object is nothing but mg plus n. Both of them are in the -x direction. Now there is no tangential acceleration at this instant because I'm just right at the top and all the forces are pointing towards the center of the circle. The only force, the net force is in the -x direction, which is toward the center. This has to be equal to m times v squared over r in the -x direction. So this tells me what the normal force is if the speed is above a given limit. So n plus mg should be equal to m v squared over r, or the normal force is equal to m v squared over r minus mg. Well, of course, in this case, if you just have a ring and your object is just moving on the ring, whereas the rod is not really holding your object, if velocity is let's say 0, the normal force turns out to be minus mg, which just doesn't make sense. I mean, here we are assuming that our mass and the rod doesn't lose contact, so that this expression is valid. Of course, the critical value at which this is applicable, so we had just said that if our object is not to fall down, then the normal force has to be larger than or equal to 0, which tells me that mv squared over r minus mg should be larger than or equal to 0. I can cancel the m's. V squared, it should be larger than or equal to g times r. So if the speed is less than this, in that case, my mass cannot just continue along this circle, but it will just fall down somewhere over. In fact, if I'm imagining that I send it over here, at some point in this region, it will just fall off. It will lose contact with the rod. It will not even be able to go up to that point.
What about the animals
Animals walking on the water. So what about them? Insects? No. No. It's due to the surface tension of the water which exerts a force. It's like for them, the surface of the water is just like a sheet of plastic which creates that force. Any questions? mg plus n is not equal to mv squared over r, but this is the total force, and at this instant, the total force is in the center. So if it is going around this circle, it has to be equal to the center. The total force has to be equal to mass times acceleration. But the acceleration of this object at this point is v squared over r, because it's doing circular motion. So on one hand, we have this expression, the total force has to be equal to this one. On the other hand, the total force has to be equal to this one, because this is the acceleration of the object, and this is the mass of the object. Now this step follows from Newton's second law, this equality. Okay, see you after 10 minutes.